Mars is not just a destination. The hardest part may be getting back. Between Mars and Earth lies a shifting distance, moving orbits, a thin but dangerous atmosphere, dust, cold, fuel, and a spacecraft that has to work perfectly at exactly the right moment. In this video, the journey moves through each layer of physics that makes leaving Mars one of the most difficult challenges humans have ever considered. If this kind of space documentary is worth your time, please like the video, subscribe to the channel, and join the journey. The broadest barrier to returning from Mars begins in open space, where Earth and Mars remain separated by a distance that never stays still. The two planets share the same star, yet they do not travel side by side. Each follows its own path around the Sun, and the space between them stretches and contracts through time. A return from Mars does not begin from a nearby shore. It begins from another moving world, across a gap that is sometimes vast, sometimes less vast, and never simple. Earth travels around the Sun at an average distance of about 150 million kilometers. Mars travels farther out, at an average distance of about 228 million kilometers. This basic difference already places Mars well beyond Earth's own orbital track. Even at the widest and calmest view, the geometry of the solar system creates a large scale for travel. Mars is not simply far away in the casual sense. It occupies another ring of motion around the Sun, and that ring is larger, longer, and slower to complete. The distance between the two planets changes because neither one waits in place. Earth completes one circuit of the Sun in 1 year. Mars takes about 687 Earth days to complete its longer path. The result is a slow and continuous rearrangement. At some times, Earth and Mars draw nearer on the same general side of the Sun. At other times, they pull far apart, with the Sun lying between their positions. In the calm language of orbital motion, this is ordinary. In the practical language of interplanetary travel, it means that the journey home never has one fixed length. Even the shape of the two paths matters. Earth's orbit is close to circular. Mars follows a more elongated ellipse, meaning that its distance from the Sun changes more noticeably over the course of a Martian year. There are times when Mars moves closer to the Sun, and times when it moves farther away. Because Earth and Mars are both in motion, and because Mars itself does not keep a constant distance from the Sun, one close approach is not the same as another. Some are relatively favourable, some are much less so. The broad number called the Earth to Mars distance hides this living variation. At the most favourable close approaches, the gap can fall to a little under 56 million kilometres. More commonly, even a relatively good alignment leaves a larger separation. At the far end of the cycle, the two worlds can stand almost 400 million kilometres apart. Between those extremes lies a wide range of ordinary separations. For long periods, Mars is simply far away. This does not make return impossible, but it gives every journey its first physical burden. Any path between the two worlds must cross tens or hundreds of millions of kilometres before Earth can again become the place of arrival. An average number can be useful, but it can also be misleading. If Mars is described as roughly this or that many million kilometres from Earth, the phrase is only a rough convenience. The real separation belongs to a moving system, not to a fixed map. The planets do not hold still long enough for a single average to describe lived conditions. In that sense, the Earth to Mars distance behaves less like the measured width of a continent, and more like the changing span between two vessels at sea, each following its own long curve. Distance in space is not empty in the human sense. It carries time with it, light, radio, and every command signal also need time to cross the gap. When Earth and Mars are relatively near, a signal still spends several minutes on its way. When they are far apart, a one-way signal can take more than 20 minutes. This delay does not explain motion by itself, but it reveals the scale of separation in a quiet and direct way. The two planets are near enough to belong to the same inner family of rocky worlds, yet far enough that even light, moving at the fastest known speed, cannot pass between them at once. This changing separation also changes the physical meaning of the word return. On Earth, return often suggests a path already familiar, a reversal of direction, a way back along a known line. In interplanetary space, return means something less direct. Earth does not remain at its outward starting position. Mars does not remain at its arrival position. The destination home continues moving through space while the departing world also continues moving. The distance between them is therefore not a static obstacle like a mountain wall or a wide ocean. It is a moving relation between two bodies that keep reshaping the span between them. From this outermost view, Mars missions appear to take place within a shared neighborhood. But the neighborhood is large enough to resist ordinary intuition. A map of the inner solar system can look compact on a page. The actual scale is severe. If Earth is imagined as one moving point on one broad track, then Mars is another moving point on a second, wider track, with dark space spread between them. Nothing in that spread reduces the separation on its own. There is no air to support wings, no road, and no fixed bridge. The first barrier is therefore not only that Mars is far away, it is that Mars is variably far away. This variability shapes any honest description of the problem, because no single number can stand for the full reality. Any statement that Mars is this many million kilometers away is only true for a moment. Soon after, it is already different. The changing gap is part of the environment itself, as real as rock, weather, or machinery. It sets the outer dimensions within which every later detail must exist. Seen from this widest region of the problem, the challenge of returning from Mars begins as a challenge of separation. A crew on Mars does not merely stand far from home. That home traces its own path around the Sun while Mars traces another. The journey back begins by accepting a simple condition of the solar system. Home is in motion across a shifting gulf, and the gulf itself forms the first layer of the barrier. Beyond the changing gap between Earth and Mars lies the deeper reason that the gap keeps changing at all. Both planets move under the gravity of the Sun. Gravity, in simple terms, is the attraction between masses. In the solar system, the Sun holds almost all the mass, and for that reason it governs the broad motion of the planets. Earth and Mars do not travel through still space by their own preference alone. They follow curved paths because the Sun continuously draws them inward, while their forward motion carries them onward. The result is orbit, a state of ongoing fall around a central body rather than a straight plunge into it. From this wider view, a journey from Mars back to Earth is not first a matter of leaving one planet and aiming at another, as if both were fixed. It is a matter of moving within the Sun's domain. Any spacecraft that travels between the two worlds must also travel around the Sun. The central field of gravity does not disappear when a vehicle rises above the ground of Mars. It remains the main shaper of motion across interplanetary space. Mars and Earth themselves are only local members of this larger order. The Sun's pull reaches everywhere in the planetary system, but its effect is not identical at every distance. A planet closer to the Sun must move faster to remain in orbit. A planet farther away moves more slowly. Earth, being closer, circles the Sun more quickly than Mars. This difference is not a minor detail. It is one of the basic rhythms of the return problem. Earth advances along its orbit at a higher average speed, while Mars traces a larger path at a lower average speed. Neither body stops, neither waits. Each remains in motion according to the same gravitational law. Yet each responds in its own way because each occupies a different orbital distance. This relation can be understood without heavy mathematics. Near the Sun, gravity is stronger and the path around it is smaller, so the orbital pace is faster. Farther out, gravity is weaker and the path is larger, so the pace is slower. Earth completes its circuit in 1 year. Mars takes nearly twice as long. Their motions are therefore coordinated but unequal. The planets return again and again to similar arrangements, yet never by standing still. They meet those arrangements only by continuing to circle the Sun. The shape of these paths also matters to the character of motion. A planetary orbit is an ellipse, a gently stretched circle, with the Sun located near one focus. Earth's orbit is only slightly stretched, so its distance from the Sun changes modestly through the year. Mars follows a more noticeably stretched ellipse, so its distance from the Sun varies more. When a planet comes a little closer to the Sun, it moves a little faster. When it drifts farther out, it moves a little slower. This is another quiet rule of orbital motion. Planets do not move around the Sun like marks painted on a turning wheel. Their speed changes along the path, even while the path itself remains stable over ordinary mission timescales. Because of this, the solar system is not a set of circular tracks with evenly marching worlds. It is a dynamic arrangement of ellipses, changing speeds, and constant solar control. A return from Mars must belong to that arrangement. Once a spacecraft departs the immediate hold of Mars, it does not enter freedom from gravity. It enters the stronger and larger pattern that already carries Mars and Earth alike. In that sense, interplanetary travel is less like crossing a void between islands and more like shifting from one current to another within the same vast sea of motion. The Sun's gravity also explains why a straight line is not the natural language of travel between planets. In everyday life on Earth, a destination often appears in terms of direct direction, in heliocentric space, meaning space centered on the Sun. Motion is inherently curved. Earth moves along a curve. Mars moves along a curve. A spacecraft released from Mars also follows a curve, because the Sun continues to pull on it every moment. The return path must therefore be understood as an orbit of its own, shaped within the same gravitational framework rather than imposed from outside it. Even the idea of standing still becomes difficult here. A body in orbit around the Sun always has a specific speed and direction relative to the Sun. Mars carries that motion. Earth carries another. Any object leaving Mars begins with Mars's solar motion already built into it. It does not start from rest in some neutral background. It begins as something already travelling around the Sun with Mars, and only then changes from that inherited motion toward a different one. The problem of return is therefore not merely to gain movement. It is to reshape motion that already exists. This broader solar setting places an important limit on simple intuition. It may seem natural to imagine that a spacecraft on Mars only needs enough force to point home and go. But home is not a still target, and the surrounding arena is not passive. The Sun commands the largest part of the system. It defines the central well of gravity within which both planets and all transfer paths must reside. A successful return has to respect this larger order at every moment, because no part of the route lies outside it. The planets themselves offer a visible expression of this rule. Earth remains bound to the Sun even while it spins and carries a moon. Mars remains bound to the Sun even while it turns beneath its thin air and small moons. Their local features differ, but their primary long-range motion is solar. At the widest physical scale that governs the journey directly, the Sun is the dominant actor, and Earth and Mars are moving worlds embedded within its field. The barrier here is not hostility or disorder. It is the calm, exact persistence of orbital motion under solar gravity, which never pauses and never simplifies itself for travellers. Within the Sun's broad field of gravity, and within the continual motion of Earth and Mars, there appears a quieter barrier that belongs not to place but to time. A return from Mars cannot begin whenever a crew feels ready. It can only begin when the two planets occupy positions that allow a practical Tao is a span of time during which departure can place a spacecraft onto a suitable transfer path toward its destination. Outside such a span, the journey does not become absolutely forbidden by the laws of nature, but it becomes increasingly costly, increasingly slow, or both. This condition arises because Earth and Mars keep moving around the Sun at different rates. Earth travels faster along its smaller orbit. Mars moves more slowly along its larger one. For a return to work efficiently, the departing vehicle cannot aim toward where Earth is at the moment of departure. It must aim toward where Earth will be when the spacecraft arrives. This is true for travel in either direction. In a return from Mars, Earth is a moving destination, and timing decides whether that destination can be reached with a manageable path. The repeating pattern of favourable alignment is governed by what is called the synodic period. This term refers to the time it takes for two orbiting bodies to return to roughly the same relative arrangement as seen from one another or from the Sun. For Earth and Mars, this period is a little more than 2 years. In practical mission planning, the interval is often described as about 26 months. This does not mean that every one of these opportunities is identical. The exact geometry differs from cycle to cycle, because Mars follows a more elongated orbit and because the positions of both planets shift continuously within their longer repeating pattern. Still, the broad rule remains steady. Efficient opportunities come only at long intervals. This creates a fundamental rhythm for Mars missions. A crew that reaches Mars cannot simply choose a day at random for departure home if the goal is to return with reasonable efficiency. It must wait for the orbital geometry to become favourable again. In some mission designs, that means remaining on or near Mars for many months after arrival, not because the surface itself requires that duration, but because the planets do. The calendar of return is written first by celestial mechanics. Human preference comes after. The idea can be pictured in plain terms. Earth is moving along one track, Mars along another. A spacecraft leaving Mars follows its own transfer orbit around the Sun. For that transfer orbit to intersect Earth successfully, the three motions must fit together. The spacecraft must leave at a time when the shape and duration of its path will carry it to the part of Earth's orbit that Earth will occupy at the same time. If departure comes too early or too late, the spacecraft may reach the correct distance from the Sun at the wrong moment, when Earth is elsewhere along its own path. In that case, the vehicle has not truly missed a place in empty space. It has missed a moving meeting. The most efficient idealized path between two circular orbits around the same central body is often described as a Hohmann transfer. This is an orbit that touches one orbit at one end and the other orbit at the other end, using relatively low energy compared with faster alternatives. Real Mars mission design is more complex than this simple model, because real planetary orbits are not perfectly circular, and missions must consider many operational details. Even so, the simple transfer remains a useful guide. It reveals why travel between Earth and Mars is tied to specific alignments and why timing matters so much. A low-energy path exists only when departure and arrival can be coordinated with the motion of both planets. This leads to one of the most important truths of the return problem. Mars can be physically reachable while Earth is not efficiently reachable from Mars at that same moment. A crew can be alive, prepared, and technically capable of launching, yet still held in place by orbital timing. The difficulty lies not in indecision, but in geometry. The sky must arrange itself into a useful pattern before the return can begin in its most practical form. The windows themselves are not single instants. They extend across limited spans of days or weeks, depending on the mission design and propulsion system. Within that span, some departure dates are better than others. A date near the center of the window may reduce the total energy required or lead to a more favorable arrival. Dates near the edges may still work, but with penalties in travel time, energy, or mission complexity. This means that return planning is not only about finding a possible month, it is about shaping a narrow band within that month, and often an even narrower preferred part within that band. The narrowness of these windows gives time a practical weight. Delays on Mars do not merely postpone the journey home by a few days in the everyday sense. A serious delay can shift a mission away from the favorable geometry altogether. Once the useful alignment has passed, the next efficient chance may not come for many months. In a crewed mission, that possibility changes the meaning of reliability, maintenance, and surface operations. Time is not a neutral backdrop. It is one of the physical conditions of return. Even faster trajectories do not free the mission entirely from this rule. A spacecraft with more powerful propulsion may widen its choices or shorten its transit, but Earth still moves, and Mars still moves. The requirement to meet a moving planet remains. Greater propulsion changes the shape of the problem, yet it does not erase the need for timing. There is always some return geometry to satisfy. Seen from this temporal region of the barrier, Mars' return depends on patience imposed by orbital law. The planets decide when efficient paths become available. Human engineering can prepare for those moments, measure them, and try to make use of them, but it cannot choose them freely. Between Mars and Earth there is not only distance and solar gravity, there is also a celestial schedule, repeating slowly, indifferent to urgency, and exact in its demands. After distance, solar gravity, and timing have defined the broad setting of a Mars return. The next barrier appears as energy. In spaceflight, energy is not only a matter of raw power in the everyday sense, it is the physical cost of changing a path that already exists. A spacecraft on or near Mars is not waiting motionless in a dark void. It already shares Mars's motion around the Sun. To come home, it must alter that inherited motion enough to leave the orbit of Mars and enter a new Sun-centered path that can meet Earth. The long return arc therefore begins not with simple movement, but with a carefully chosen change in movement. This point is easy to miss because rockets seem, at first glance, to be devices that merely add speed. In interplanetary travel, the deeper task is subtler. The spacecraft already travels around the Sun because Mars does. Mars moves along its orbit at about 24 kilometers per second. Earth, on its smaller orbit, moves faster at about 30 kilometers per second. These numbers describe the planets themselves, but they also describe the motion any departing vehicle inherits at the moment it leaves a planetary environment. A returning craft starts as something that is already moving around the Sun with Mars. Its path home must be built from that fact. For an efficient return from the orbit of an outer planet to the orbit of an inner one, the spacecraft usually does not need a Sun-centered path with greater orbital energy. It needs less. In plain terms, it must shift from a larger solar orbit toward a smaller one, The standard low-energy picture is an ellipse that touches Mars's orbital distance at its far point from the Sun and reaches Earth's orbital distance at its near point. The Sun remains at one focus of this ellipse, as it does for all ordinary planetary orbits. The return path is therefore not a straight descent toward Earth. It is a new solar orbit, narrower than Mars's and stretched inward toward Earth. To create that inward transfer, the spacecraft must reduce its orbital energy around the Sun at the point where it departs from Mars's distance. This may sound strange at first, because rockets consume stored chemical or electrical energy to perform the maneuver. Yet the result of that effort, measured relative to the Sun, is commonly a slower path around the Sun, not a faster one. The vehicle continues in the same general direction of solar motion, but with less sun-centered speed than Mars has. Once that happens, the spacecraft no longer stays on Mars's broader track. The Sun's gravity then shapes the new ellipse so that it falls inward toward Earth's orbital region. This is one of the quiet, counterintuitive truths of returning from Mars. The mission must spend propulsive energy in order to shed orbital energy. The rocket works hard, but the desired long arc is one in which the spacecraft circulates around the Sun on a lower energy path than the one Mars follows. The engines do not fight the Sun. They set up the conditions under which the Sun reshapes the trajectory. Engineers often describe such maneuver demands in terms of change in velocity, meaning the amount by which the spacecraft must alter its motion. This idea includes direction as well as speed. For a Mars return, the critical issue is not merely how much faster the craft can go, but how precisely it can leave Mars with the right new sun-centered motion. A large change in the wrong direction can be less useful than a smaller change in the correct one. In that sense, returning from Mars is a problem of geometry joined to energy. The spacecraft must change its motion enough, and in the right way, to trade one solar orbit for another. The most energy-efficient idealized route between Mars's orbit and Earth's orbit belongs to the same family of transfer paths already used to understand travel outward from Earth. This family is often called the Hohmann transfer. For a return from Mars, the logic is reversed. Instead of raising the far end of an orbit outward toward Mars, the mission lowers the near end inward toward Earth. The vehicle departs Mars's orbital distance, enters an elongated ellipse around the Sun, and then coasts along that arc until it reaches Earth's orbital distance at the proper time. Most of the journey, once the main maneuver is complete, is not powered flight. It is free fall within the Sun's gravitational field. That long coasting phase is important because it reveals where the energy burden truly lies. The spacecraft does not need to fire continuously all the way home in a conventional chemical mission. Rather, it needs a decisive maneuver that places it on the correct return ellipse, plus smaller corrections later. This means the mission concentrates a large part of its propulsive demand near departure. The craft must carry or create the means to perform that maneuver before the long, quiet coast can begin. There is also a trade between time and energy. A return path that uses relatively little propellant tends to be slower than more aggressive alternatives. A mission can, in principle, shorten travel time by choosing a higher energy trajectory, but that usually demands a larger change in velocity and therefore more propellant or a different propulsion system. This trade is central to the difficulty of coming home from Mars. Fast returns are appealing for human health, supplies, and exposure to space radiation. Yet faster paths usually make the energy problem heavier rather than lighter, because rockets must push by throwing mass away. Required maneuver energy does not remain an abstract number. It becomes stored propellant, tank volume, engine performance, structural support, and mission risk. Each increase in needed maneuver can widen the problem. More propellant adds mass. More mass can require more propellant to move that added mass. Designers work constantly against this compounding effect. Even before the vehicle is examined in detail, the logic is already present in the long return arc itself. The physics of orbital change places a direct burden on everything the mission must carry. Seen from this region of the problem, returning from Mars is difficult not because space resists motion with air or friction, but because orbital motion is exact. A spacecraft must leave Mars's sun-centered path and enter another one that reaches inward to Earth. To do that efficiently, it must spend precious maneuver capability to become, in the solar sense, a little slower. From that carefully chosen reduction comes the long inward ellipse. The broad return arc is therefore a matter of disciplined energy use, where the cost of coming home is written first in the shape of an orbit around the Sun. As the return problem moves inward from the broad orbit of the Sun, Mars begins to stand out as a local world with its own gravity. The planet is much smaller than Earth and much smaller than the Sun, yet it still creates a distinct region around itself where its pull becomes the main immediate influence on nearby motion. This region does not have a hard visible edge. It is not marked by a wall, a ring, or a sudden break in space. Instead, it is a gradual transition in gravitational dominance. Far from Mars, the Sun remains the stronger guide for a spacecraft's path. Closer to Mars, the planet's own pull increasingly shapes what that spacecraft does. The return journey from Mars must begin within this smaller gravitational domain. A useful term for this local domain is sphere of influence. This does not mean that gravity from other bodies disappears outside or inside a neat sphere. The Sun always exerts gravity, and so does Earth. Though Earth's pull is usually very small at Mars, the term simply describes the region where Mars becomes the most practical reference for local trajectory design. Within that region, a spacecraft can be said to orbit Mars in a meaningful operational sense. Outside it, interplanetary motion around the Sun again provides the more useful picture. The change between these views is gentle in physics, but sharp in mission planning. It marks the shift from a solar return arc to the immediate task of leaving a planet behind. Mars is often described as smaller and weaker than Earth, and in one sense this is true. Its mass is only about 1/10 that of Earth. Its surface gravity is a little more than 1/3 of Earth's. This lower gravity makes ascent easier than ascent from Earth, but it doesn't make ascent easy in any simple sense. A spacecraft on Mars still rests deep inside a gravitational well, meaning a state in which energy is required to climb out. The well is shallower than Earth's, yet it remains a real barrier. To return home, the mission must first escape Mars before it can fully belong once more to a sun-centered path toward Earth. This local gravitational well has a quiet but important consequence. A return from Mars is not one maneuver only. It is not a simple act of leaving the surface and then somehow being on the way to Earth in a single step without distinction. The spacecraft must first gain enough energy to rise into or through a useful Mars-centered trajectory. Only from that local state can it then depart Mars in the correct direction and at the correct speed to enter the larger solar arc homeward. In practice, these two tasks may be closely linked or combined, but physically they are still different. One belongs to Mars as a planet, the other belongs to the Sun and the wider solar system. Seen from space, Mars rotates beneath a very thin atmosphere and a landscape of plains, volcanoes, basins, and canyons. Yet from the present region of the problem, the surface details remain secondary. What matters first is that Mars is a moving gravitational center with a finite escape speed. Escape speed is the minimum speed needed without further propulsion for an object to leave a body's gravity permanently from a given distance. For Mars at the surface, this value is about 5 kilometers per second. That number is much lower than Earth's, which is one reason Mars is considered a possible departure world for future crews. Still, 5 kilometers per second is not a small demand. It represents a large change in motion for a machine that must launch from another planet carrying life support, guidance, structure, and whatever propellant has been prepared for the journey. A further quiet difficulty comes from the fact that escaping Mars is not enough by itself. A spacecraft can leave Mars and still fail to return efficiently to Earth. If it departs in the wrong direction, or with the wrong excess speed beyond escape, it may enter a poor orbit around the Sun, one that misses Earth, takes too long, or demands major correction. This means that the boundary around Mars is not just a barrier to be crossed. It is a place where local departure conditions determine the quality of the entire interplanetary return. The craft must leave Mars not merely free, but properly aimed within the larger geometry already established by planetary motion. Mars also has 2 small moons, Phobos and Deimos. Their mass is tiny compared with that of the planet, and for the broad return problem, they do not dominate trajectory design in the way Earth's moon can influence some Earth missions. Still, their presence is a reminder that Mars is a complete local system, not just a point in space. A departing vehicle moves through a real planetary environment with its own minor companions, its own day, and its own local gravitational order. Even when these smaller influences are modest, they belong to the practical truth of operating around another world. Because Mars is smaller than Earth, orbits close to it differ in useful ways. A spacecraft can circle Mars with lower speed than is required in low orbit around Earth. Maneuvers to enter or depart orbit are correspondingly different. This can help mission planners, but it also narrows margins in some respects. Lower gravity offers less natural hold. Orbital conditions are tied closely to altitude and local mission needs. A return architecture must therefore decide whether the ascent vehicle rises straight into escape, pauses in orbit, or uses some combination of staged maneuvers. These are engineering choices, but all of them arise from the same physical fact. Mars is large enough to trap a spacecraft, yet small enough that designers may exploit several different paths out of its hold. From the standpoint of a crew waiting to leave, the most important truth in this region is calm and exact. Mars is not merely the place they stand, it is a local gravitational world embedded inside the greater field of the Sun. To return home, the mission must first stop belonging only to Mars. The vehicle must climb out of a shallower well than Earth's, but a well nonetheless. It must cross a region where Mars still governs local motion, and it must do so with a departure state precise enough to matter far beyond that region. Here the return problem narrows from the vast spacing of planets to the immediate influence of one planet. The journey home becomes, in its next layer, the act of leaving Mars not only physically, but dynamically, by passing from the grip of a smaller world back into the larger order of interplanetary flight. Above Mars, the atmosphere does not end at a clean line. It grows thinner with height, becoming less like everyday air and more like a scattered population of atoms and molecules spread through near space. This outermost part of the Martian atmosphere forms the next barrier to returning home. At first it may seem too slight to matter. Mars has only a thin atmosphere compared with Earth, and its high air is thinner still. Yet even here the atmosphere remains physically real. A returning mission must pass through it on the way up, and nearby spacecraft must work within its reach. The thin edge of Martian air is therefore not empty space. It is a transition zone where gas is sparse, but not absent. in the broadest sense. An atmosphere is the layer of gas held to a body by gravity. Mars retains such a layer because its gravity is strong enough to keep gas near the planet over long periods, even though part of that gas also leaks away to space. The uppermost region becomes so rarefied that particles travel long distances between collisions. This outer zone is often called the exosphere. Below it lies the thermosphere, where sunlight and energetic particles from space can heat the gas strongly even though the gas itself is extremely thin. These names help describe the structure, but the practical meaning is simpler. Near the top of the atmosphere, Mars fades into space gradually rather than abruptly. This gradual fading matters because spacecraft do not move by labels. They move through actual density. Even a very small amount of gas can matter when a vehicle travels at high speed. Drag, meaning the resisting force produced by motion through gas, depends on density, speed, shape, and orientation. As density falls, drag weakens. Yet at orbital and near-orbital speeds, weak drag is not the same as no drag. A spacecraft passing low over Mars can still lose energy to the upper atmosphere. A craft climbing away from the planet can still feel a small aerodynamic burden before it reaches the cleaner vacuum above. The upper atmosphere also matters because heating begins there in physical terms. Heating in fast flight does not come from simple rubbing in the ordinary sense. It comes mainly from the compression and disturbance of gas in front of the vehicle, and from energetic interactions between gas particles and the vehicle surface. Where gas exists, these effects begin. Around Mars, the amount is far smaller than around Earth for many ascent conditions, because the atmosphere is much thinner. Even so, the thin edge of air still belongs to the thermal environment through which a vehicle must rise. For a return from Mars, this means that the planet presents neither the full aerodynamic challenge of Earth nor the near-total absence of atmosphere found on the Moon. Mars lies between these extremes. Its air is too thin for ordinary aircraft flight at the surface without special design, yet thick enough to shape entry, descent, landing, and the first part of ascent. In the uppermost layers, the atmosphere becomes tenuous, but it still creates a region where spaceflight and aerodynamics overlap. Returning from Mars therefore involves not just rocketry in vacuum, but rocketry through a fading envelope of gas. This overlap complicates the boundary between atmospheric flight and orbital flight. A launch vehicle does not suddenly switch from one regime to the other at a single universal height. Instead, the character of motion changes continuously as pressure and density fall. Lower down, aerodynamic forces can influence stability, structural loads, and the shape of the ascent. Higher up, those forces weaken until gravity and pure orbital mechanics dominate almost completely. The thin edge of the atmosphere is the long upper part of that transition. It is the last portion of a Mars that still acts through air. Because the upper atmosphere is so tenuous, it can be tempting to think of it as negligible for mission design. In reality, engineers pay close attention to it. Low Mars orbits can slowly change under the influence of atmospheric drag, especially when an orbiter dips closer to the planet. Even small density at high altitude can alter a path over time. For a crewed return architecture, this matters in several ways. It affects how long a vehicle can safely remain in a very low orbit. It affects predictions of ascent performance during the final atmospheric segment. It also affects the accuracy with which guidance systems can anticipate the motion of a vehicle rising through the last wisps of air. The thin edge of the Martian atmosphere also has a chemical and physical character different from denser lower layers. In the lower atmosphere, frequent collisions keep the gas more mixed and more fluid in its behavior. Higher up, collisions become rarer and individual particles matter more. Some particles are energetic enough to escape Mars altogether. Others are ionized, meaning they carry electric charge and can interact with the solar wind and magnetic fields carried through space. The upper atmosphere of Mars is therefore not only the top of the weather-bearing air, it is also part of the long exchange between the planet and surrounding space. A return mission does not need to study that exchange in full to feel its consequences, but it must respect the fact that Mars has no sharp lid on its atmosphere. From the perspective of a vehicle on the way home, the thin edge of the atmosphere is a place of diminishing resistance. As the craft climbs, density falls rapidly, drag declines, and aerodynamic control becomes less important. At the same time, the vehicle is still under Mars's gravity and still trying to gain the speed and direction needed for orbit or escape. This means the upper atmosphere participates in a subtle contest. The rocket must keep climbing strongly enough that the remaining gas no longer costs meaningful performance, while also shaping its path for the spaceflight phase beyond. The atmosphere is fading, but the mission cannot ignore it until it is gone in practical terms. Mars does not hand a departing spacecraft cleanly from ground to vacuum. It places between them a broad thinning veil, one that is slight in mass but significant in effect. The outermost air of Mars marks the final reach of the planet as an atmospheric body. Here, on the edge between air and space, returning home still means rising through matter, however sparse, before the journey can belong fully to space alone. Above the already thin lower air of Mars, the upper atmosphere does not remain steady from day to day or season to season. It expands, contracts, warms, cools, and shifts in composition under the combined influence of sunlight, dust, and the changing geometry of the Martian year. This restless behavior forms the next barrier to returning from Mars. A launch vehicle rising through the upper air does not pass through a fixed medium. It passes through a region whose density and temperature can vary with time, sometimes gently and sometimes more strongly, in ways that matter to prediction and planning. The upper atmosphere of Mars is shaped first by energy from the sun. Short-wavelength sunlight, especially ultraviolet and extreme ultraviolet radiation, is absorbed at high altitudes. This absorption heats the gas and can also ionize it, meaning that some atoms and molecules lose electrons and become electrically charged. Even though the upper air is extremely sparse, its temperature can become high in a physical sense because the few particles present carry substantial energy. This does not mean that the upper atmosphere would feel warm in the ordinary human sense. Since there are too few particles to transfer heat efficiently to skin or metal in the way dense air does, it means that the particles themselves are energetic and that the gas can expand upward in response. When solar input rises, the upper atmosphere tends to puff outward. At a given altitude, density may increase because warmer gas occupies more vertical space. When solar input falls, the upper atmosphere can contract. These changes do not transform Mars into a thick-aired world, but they do alter the height and density structure of the region through which spacecraft travel. The Sun therefore acts not only as the central gravitational anchor of the return journey, but also as a driver of atmospheric variability in the high sky above Mars. Season also matters strongly. Mars has 4 seasons, like Earth, but they are longer because the Martian year is longer. The planet's orbit is also more elongated, so seasonal differences in received sunlight are more uneven between hemispheres than they are on Earth. Southern summer occurs when Mars is closer to the Sun, making that season warmer and more energetic than northern summer. This seasonal asymmetry affects the whole atmosphere from lower levels upward. As the lower and middle atmosphere change, the upper atmosphere responds through waves, circulation, and heat transport. The result is that high-altitude density does not stay constant throughout the Martian year. It follows a seasonal pattern, overlaid with shorter-term fluctuations. Dust is one of the most important reasons this upper atmosphere becomes difficult to treat as stable. Mars is a dusty planet, and its fine mineral particles can be lifted by winds into the air. During local and regional dust events, and especially during larger storms, sunlight is absorbed by this suspended dust in the lower and middle atmosphere. That added heating changes the thermal structure below, which then influences the air above. The atmosphere can expand upward as a connected system. At altitudes relevant to orbiting spacecraft or to the upper part of an ascent path, density can rise above what a quiet season would suggest. In simple terms, storms near the ground can alter conditions much higher up than ordinary intuition might expect. This link between dust and high-altitude density is one of the reasons Mars missions must treat the atmosphere as an interconnected whole. The upper atmosphere is not isolated from the rest of the planet's air merely because it is high. Waves and tides move through it. Heating in one region can affect another. Dust storms can therefore change more than visibility or surface operations. They can alter the very shape of the upper atmospheric envelope. Measurements from modern Mars missions indicate that these responses are real, though the exact size of the effect depends on altitude, season, local time, and the strength of the storm. Observations indicate a clear connection between dusty periods and increased density in the upper atmosphere. It remains uncertain in detail how large the response will be for every future event at every place and time. Local time matters as well. The day-side upper atmosphere receives direct solar energy, while the night side does not. This produces differences in temperature and density between day and night, though circulation partly redistributes the energy. A spacecraft rising from the surface during one local time may encounter a somewhat different upper atmospheric structure than a similar vehicle rising during another. These differences are not usually so large that they redefine the mission by themselves, but they matter for accurate modelling. Precision grows more important when performance margins are narrow. Solar activity introduces another source of change. The Sun does not emit high-energy radiation at a perfectly constant rate. It varies over its activity cycle and during shorter-lived energetic events. Mars also lacks a strong global magnetic field like Earth's, so its upper atmosphere interacts with the solar wind in a different and more direct way. Charged particles and changing solar conditions can affect ionization, heating, and the escape of atmospheric particles to space. For a return mission, the most immediate concern is not the long history of atmospheric loss, but the operational reality that upper atmospheric conditions are influenced by the state of the Sun as well as by conditions within Mars's own climate system. All of this makes forecasting difficult. Engineers do not need perfect knowledge of every particle in the upper atmosphere, but they do need reliable ranges. They need to know how dense the air may be at certain heights, how that density can change with season, and how dust or solar conditions might shift the expected values. This is why atmospheric models for Mars include not only average conditions, but also seasonal and dusty scenarios. A launch from Mars must be planned against variability, not against a single ideal profile. The upper atmosphere of Mars therefore behaves less like a fixed shell and more like a breathing boundary. It rises and falls with sunlight, season, and dust. It thins and thickens at given heights according to patterns that are understandable in broad outline but not perfectly predictable in every moment. For a crew hoping to return home, this means that the high sky above the launch site is not an unchanging corridor. It is a moving atmospheric structure whose variability must be measured, modelled, and respected before the ascent can safely pass through it. Below the changing upper atmosphere, the deeper air of Mars forms a more familiar but still unusual weather world. Here the gas is dense enough to behave as a true moving fluid across the planet, yet still far thinner than the air near sea level on Earth. This lower atmosphere becomes the next barrier to returning from Mars because it is the part through which an ascent vehicle must rise directly from the ground. It presses on the surface, flows over plains and crater rims, moves heat from day to night, and creates the winds and pressure changes that shape launch conditions. A mission leaving Mars does not lift from still vacuum, it lifts through a working sky. The lower atmosphere of Mars is composed mostly of carbon dioxide, with smaller amounts of nitrogen, argon, and traces of other gases. This composition matters because carbon dioxide behaves differently from the nitrogen and oxygen-rich air of Earth. Under Martian conditions, it participates in a seasonal cycle in which part of the atmospheric mass can freeze onto the polar regions during winter and later return to the air as spring sunlight warms those deposits. The atmosphere of Mars is therefore not only thin, it also changes in total mass over the course of the year more strongly than Earth's atmosphere does. This seasonal breathing affects pressure across the planet and contributes to the shifting background through which any return launch must pass. Near the surface, the atmospheric pressure on Mars is low, commonly around only a small fraction of the pressure at Earth's sea level. Because the air is so thin, it produces much less lift and much less drag than Earth's atmosphere for the same speed and shape. This reduces some aerodynamic burdens during ascent, but it also removes some of the helpful aspects of dense air. Control surfaces are less effective. Convective cooling, meaning heat transfer by moving air, is weaker. Engines and structures cannot rely on the atmosphere in the same way. Aircraft or launch systems on Earth often do. Mars offers too much air to ignore and too little air to treat as a strong partner. The lower atmosphere also responds strongly to the cycle of day and night. Mars rotates in a little more than 24 hours, giving the planet a daily rhythm similar in length to Earth's, but different in consequence because the air is thin and the surface often changes temperature quickly. After sunrise, the ground warms and heats the air just above it. After sunset, the ground loses heat rapidly to space, and the air near the surface cools again. These daily temperature swings can be large, especially in clear conditions and dry terrain. As the lower atmosphere warms and cools, it expands and contracts, rises and settles, and sets local winds into motion. Those winds are not constant over the planet. They depend on local time, season, latitude, elevation, and terrain. On Mars, the surface relief is enormous. The planet contains volcanoes taller than any on Earth, and basins lying far below the mean level of the terrain. Such topography channels air, produces slope winds, and influences regional circulation. Cold air can flow downslope at night. Daytime heating can drive upslope flow in some regions. Broad plains can support steady horizontal winds, while crater walls and rough ground can create local turbulence. This means that the lower atmosphere is not one simple global layer. It is a planet-wide circulation system shaped continuously by the land beneath it. One of the most important large-scale patterns comes from the fact that Mars has strong differences in elevation. Surface pressure is higher in low basins and lower on high plateaus, just as it is lower on mountains on Earth. For a launch vehicle, this matters because the same rocket placed at different Martian elevations begins in different atmospheric conditions. A site deep in a basin may have somewhat thicker air and slightly greater aerodynamic effects. A site high on a plateau may offer thinner air, but also a different thermal and wind environment. There is no single Mars launch atmosphere valid everywhere on the planet. The weather of the lower atmosphere also includes pressure tides driven by sunlight. These are regular rises and falls of pressure over the course of the day, caused by heating that moves through the atmosphere in a wave-like pattern. On Mars, these tides can be relatively important because the atmosphere is thin and strongly responsive to solar heating. Instruments on the surface have shown that pressure at one location can rise and fall in predictable daily rhythms. For launch planning, such patterns are useful because they are not purely random. They can be measured, modelled, and used to choose more favourable times for ascent. Yet even a predictable rhythm must still be respected, because a small pressure difference in a thin atmosphere can matter to performance estimates and aerodynamic loads. Temperature in the lower atmosphere also affects engine and vehicle behaviour indirectly. Colder air is denser than warmer air at the same pressure level, and density influences drag. Temperature also affects the condition of tanks, seals, materials, and ground systems before launch. On Mars, the lower atmosphere often carries intense cold, especially during the night and near dawn. A vehicle standing ready for departure must endure that cold, while also being prepared for the warmer and more turbulent period after sunrise. The weather is therefore not only an issue for flight itself, it shapes the hours of preparation before the engines begin. Wind deserves special care because even in thin air it can matter during the earliest part of ascent. A launch vehicle is slowest just after leaving the ground and is therefore most exposed to being pushed sideways by moving air. The thin atmosphere reduces the absolute force compared with Earth, but the rocket may also be lighter, narrower in margin, and operating in an environment where precision matters greatly. Crosswinds, gusts, and local shear, meaning a change in wind speed or direction with height, can all influence guidance and structural demands. Mars does not need Earth-like air to make winds operationally significant. It only needs enough moving air at the wrong moment. The lower atmosphere of Mars is therefore a restrained but active meteorological system. It is thin, carbon dioxide rich, strongly shaped by the ground, and alive with daily and seasonal change. It creates pressure cycles, temperature swings, and winds that vary from place to place and hour to hour. A spacecraft returning home must rise through this air from the first instant of launch. The sky above the vehicle is not dense, but it is not passive. It remains part of Mars, and it takes part in the difficulty of leaving. Within the lower atmosphere of Mars, one material gives the air much of its changing character. That material is dust. It is made of very fine particles of broken rock and mineral matter, small enough to be lifted, carried, and held aloft by Martian winds. This suspended dust forms the next barrier to returning from Mars because it changes the sky through which a launch must rise, and the working conditions under which that launch must be prepared. The air of Mars is thin, but when dust enters it in large amounts, the planet's meteorology becomes a system not only of gas and temperature, but of gas and solid particles moving together. Martian dust is not the same as ordinary sand. Sand grains are larger and tend to hop or creep close to the ground when winds are strong enough. Dust consists of finer material, often measured in only a few micrometers across. Because the particles are so small, they can remain suspended in the air for long periods once they are lifted. This gives Mars its frequent hazy appearance and allows local disturbances to grow into broader atmospheric events. A particle that is too small to notice by eye at arm's length can still matter when billions of such particles fill the sky. The lifting of dust begins near the surface, where winds interact with loose material. In many cases, the wind first moves larger grains close to the ground. Those grains then strike the surface and help release finer particles into the air. On Mars, this process is shaped by the low atmospheric density. Thin air has less force available for a given wind speed than dense air on Earth, so dust lifting can seem surprising. Yet the planet's dry, fragmented surface and frequent winds still allow large amounts of fine material to become airborne. Once suspended, the dust no longer belongs only to the ground. It becomes part of the atmosphere itself. The amount of dust in the Martian sky can vary greatly. Sometimes the air remains only lightly hazy, allowing sunlight to reach the ground with modest weakening. At other times, local dust storms form, lifting enough material to turn a region visibly opaque and to change temperature patterns in the surrounding atmosphere. Some of these storms remain limited in size. Others grow into regional events that cover broad parts of the planet. On occasion, storm activity expands so widely that much of Mars becomes wrapped in airborne dust. These larger storms are often called planet-encircling dust events rather than truly global storms, because the dust does not form a perfectly uniform shell around the entire world at once. Even so, the scale can become enormous. Dust changes sunlight first by scattering and absorbing it. Scattering redirects light in different directions, softening shadows and brightening some parts of the sky, while dimming the direct beam from the sun. Absorption converts part of the incoming light into heat within the atmosphere. Together, these effects alter what reaches the surface and what happens above it. The ground may receive less direct solar energy, while the atmosphere itself becomes warmer at dusty levels where the particles absorb radiation. This can change temperature gradients, alter wind patterns, and feed back into the development of the storm. Dust on Mars is therefore not only something carried by the weather, it helps shape the weather. This effect on light has immediate meaning for surface operations before launch. Visibility can decline from clear distant views to a muted reddish haze in which the horizon softens and surface contrast fades. In stronger storms, dust can obscure landmarks, reduce the usefulness of optical navigation systems, and complicate visual inspection of equipment. Cameras, sensors, and human observers all depend on light that reaches them in a stable way. Airborne dust makes that light weaker, redder, more diffuse, and less reliable. A mission preparing for ascent must therefore consider not only the dynamics of the rocket, but also the changing ability to see, measure, and confirm. The weakening of sunlight also affects power. Solar panels on Mars can lose output for two reasons during dusty periods. First, the dusty atmosphere reduces the sunlight arriving from above. Second, settling dust can accumulate on the panel surfaces themselves, reducing transmission further. For a launch system that depends partly or wholly on solar energy during preparation, this becomes a serious operational concern. Power margins shrink, charging times lengthen, heating, communications, pumping, and general system readiness may all suffer. A storm does not need to damage the vehicle directly to delay a return. It may simply reduce the energy available to prepare the vehicle safely. Dust also interacts with machinery in more direct ways. Fine particles can adhere to surfaces, especially where static electrical effects, rough textures, or seals provide places for them to cling. Mars is dry, and the dust is often chemically reactive and mechanically persistent. It can coat radiators, windows, joints, instruments, and connectors. Moving parts may experience greater wear if dust enters them. Filters can load with particles. Transparent surfaces can lose clarity. Thermal control can shift because dark or dusty coatings absorb sunlight differently from clean ones. None of this means that Mars dust makes machinery unusable by definition. It means that hardware meant to support a return must be designed and operated as if dust will be present, because over time it almost certainly will be. The electrical behavior of dust remains an area of active study. Observations and experiments suggest that moving dust can acquire electric charge through frictional and contact processes, especially in dry, turbulent conditions. It remains uncertain how strong large-scale electrical effects become during all Martian dust storms, and how often they pose significant risk to future human systems. What is clear is that the dust is fine, adhesive, and persistent enough to deserve careful mitigation even without assuming extreme electrical behavior. Dust in motion also creates uncertainty in weather prediction. A calm period can give way to lifting events that begin locally, influenced by terrain, sunlight, and regional circulation. Some disturbances fade quickly, others organize and expand. This makes storm forecasting on Mars a matter of probabilities and trends rather than perfect certainty. Observations indicate clear seasonal patterns, with stronger storm activity tending to occur during particular parts of the Martian year, especially when the southern hemisphere receives more intense sunlight. Even then, the exact timing, growth, and duration of a given storm remain difficult to predict in full detail. For a crew waiting to leave Mars, airborne dust transforms the atmosphere from a thin launch medium into a changing operational hazard. It alters light, redistributes heat, reduces visibility, weakens solar power, and settles onto the very systems needed for departure. It can remain local, spread regionally, or swell until much of the planet is under haze. In this region of the return problem, the barrier is not only wind or air pressure, it is the presence of fine mineral matter made mobile by weather, turning the sky itself into part of the challenge of getting home. At the surface of Mars, the return problem reaches the ground itself. Here, gravity is no longer an abstract property of a planet viewed from space. It becomes the steady downward pull acting on the launch vehicle, the crew, the tanks, the engines, and every tool resting on the surface. At the same time, the planet's terrain stops being a map of broad regions and becomes the actual shape of the place from which ascent must begin. This combination of surface gravity and uneven land forms the next barrier to returning from Mars. A vehicle cannot leave from a diagram. It must leave from a real patch of another world. Mars has a surface gravitational acceleration of about 3.71 meters per second squared, a little more than 1/3 of Earth's. This lower gravity is often described as an advantage for departure, and in an important sense it is. A rocket on Mars needs less upward force to lift its own weight than an equivalent rocket on Earth. The required escape speed is lower, and the climb away from the planet begins from a shallower gravitational well. Yet lower gravity does not remove the difficulty of ascent, it only changes its scale. The vehicle still has mass, and mass is the measure of how strongly matter resists changes in motion. A heavy spacecraft on Mars weighs less than it would on Earth, but it is not easier to accelerate in every respect simply because it is lighter in weight. Its inertia remains the same. This distinction between weight and mass becomes important as soon as the engines begin to push. Weight is the downward force caused by gravity. Mass is the amount of matter that must be accelerated. Mars reduces the first, but not the second. A return vehicle still requires engines, structure, control, and stored propellant appropriate to its mass. The planet helps by pulling downward less strongly than Earth, but it does not make the spacecraft a small or effortless thing. The rocket must still gain speed, hold stability, and rise with enough performance margin that the ascent remains controlled. The lower gravity also changes the experience of working on the ground before launch. Equipment presses less strongly into the surface. Structures carry different loads through their legs or supports. Crew and machines can move large objects more easily in terms of lifting weight, but those same objects can still be awkward to start, stop, or steady because their mass has not changed. A tall vehicle standing on Mars may therefore feel, in engineering terms, both helped and challenged by the environment. Gravity is weaker, which eases some static loads, but the machine still needs a stable stance and careful control because its full inertia remains present. The terrain beneath that machine is far from uniform. Mars is a planet of great topographic contrast. Its southern hemisphere stands, on average, much higher than its northern lowlands. Vast volcanic rises, giant impact basins, ancient crater fields, lava plains, canyon systems, and wind-shaped surfaces all contribute to a landscape of strong relief. Even within a broadly suitable region, local ground can vary from smooth and open to broken and hazardous across short distances. For a return launch, this matters because ascent begins from one chosen site, not from the average character of a hemisphere. A launch site must offer more than room. It must offer geometric calm. The ground should be level enough that the vehicle can stand upright within safe limits. If the surface tilts too much, the rocket begins its ascent already misaligned with local vertical. Guidance can compensate for only so much initial error before loads, clearances, and control demands become undesirable. A sloping site also changes how propellant settles in tanks before ignition, how support structures bear weight, and how access systems meet the vehicle. For these reasons, mission studies for human-scale Mars operations generally favor terrain that is broadly smooth and gently sloped, rather than rugged, heavily cratered, or densely strewn with obvious hazards. Even a modest slope becomes more significant when combined with the scale of a launch vehicle. A small difference in height across a few meters can translate into a meaningful lean for a tall machine. That lean may still be correctable, but corrections consume margin. The same is true of nearby topography. A launch site in rough terrain can create line-of-sight limitations for instruments and communications, complicate approach paths for supporting vehicles, and leave less room for safe separation between the rocket and natural obstacles. Ground that appears acceptable for a rover or a small lander may not be equally acceptable for a crewed ascent system. Rocks, ledges, shallow depressions, and fractured ground all contribute to this problem even before the detailed soil behavior is considered. A launch vehicle does not merely need a place where it can touch down or stand temporarily. It needs a place where its base geometry, clearances, and orientation remain predictable. Uneven terrain can concentrate loads into one side of the structure, complicate leveling, or force the use of pads and supports that add mass and operational complexity. The challenge here is still geometric rather than material. The shape of the land itself can make a departure site good or poor before one even asks how firm the soil may be. Mars also complicates site selection through visibility and scale. Orbital images can reveal large hazards clearly, and laser altimetry can map broad slopes and elevations across the planet. Yet a safe launch site depends on local detail as well as regional character. A site may appear smooth at one mapping scale and still contain problematic roughness at a smaller one. For this reason, Mars site evaluation depends on multiple levels of observation, from global topography to local imaging. The broad terrain context matters because it controls climate and access, but the local surface shape matters because it controls whether the vehicle can stand and rise safely. Surface gravity and terrain also interact during the first seconds of ascent. As the engines produce thrust, the vehicle must transition from resting on the ground to climbing freely away from it. In lower gravity, That transition can occur with less required thrust than on Earth, but it still depends on beginning from a stable posture. A rocket leaving uneven ground is more vulnerable to tilt, side load, and control disturbance precisely when its speed is low and its margin for error is smallest. The first meters matter greatly because they determine whether the climb begins cleanly. From this region of the return problem, Mars presents a sober physical truth. The planet is easier to leave than Earth in terms of gravity, but it is still a real world with real slopes, real relief, and no guarantee of a naturally ideal launch pad. Returning home begins not only with engines and trajectories, but with a vehicle standing on another planet under another gravity, on terrain that must be gentle enough, open enough, and stable enough for departure to start in order. Beneath the launch vehicle, below the thin air and the moving dust, lies the material from which the immediate surface of Mars is made. This material is commonly called regolith, a word used for the loose layer of broken rock, mineral fragments, dust, and soil-like matter that covers solid bedrock. On Mars, regolith forms the next barrier to returning home because it is the substance that must support the vehicle before launch and withstand the force of the engines during departure. A rocket does not leave from atmosphere alone, it leaves from ground, and the ground has its own physics. Martian regolith is not uniform across the planet. In some places it appears as fine dust over broad plains. In others it includes sand, crusted surfaces, pebble fields, rock fragments, and layered soil with different properties at different depths. Some landing sites studied by spacecraft show loose surface material over firmer layers. Others reveal shallow crusts, clods, or soils that hold together more strongly than dry dust alone would suggest. This variety matters because the surface beneath a launch vehicle is not a simple powder of one constant texture. It is a natural material shaped by impacts, volcanic history, wind activity, chemical alteration, and long exposure to cold and dryness. The size of the particles in this regolith affects how the material behaves under load. Very fine grains can pack densely, but may also be easily disturbed at the surface. Coarser grains can allow spaces between particles and produce different patterns of settling and shear. A soil made of many different grain sizes may behave differently from one made mostly of one size. Particle shape matters too. Angular grains, with sharp edges and irregular faces, can interlock more strongly than smooth, rounded grains. Mars has abundant mechanically broken material, and many particles are not worn into smooth shapes as river pebbles often are on Earth. This tends to give the regolith frictional strength, meaning resistance to sliding within itself. That internal resistance is important because a launch vehicle presses downward through its landing legs or support base. The ground must bear that pressure without collapsing excessively. Engineers describe this capacity as bearing strength, the ability of the soil to support a load. If the regolith is too weak, the legs may sink unevenly, tilt the vehicle, or cause local failure beneath one side. If it is stronger, the vehicle can remain level and stable through fueling, checkout, and ignition. Mars regolith is therefore not only scenery, it is the foundation of the launch system in the literal sense. The strength of regolith does not depend only on particle size and shape. It also depends on how tightly the particles are packed, how much small material fills the gaps between larger grains, and whether weak cementing forces hold grains together. On Mars, salts, frozen water in some environments, and thin films of adsorbed water under local conditions may contribute to cohesion, meaning a tendency for particles to stick together. Observations from landed missions indicate that some Martian soils are not perfectly loose and dry in the simplest sense. they can form crusts or clumps and may resist digging in ways that show modest cohesion. It remains uncertain how such properties vary at every potential human landing site and with depth below the surface. But the general lesson is clear. Martian regolith can behave as a structured geotechnical material rather than as a simple layer of dust. Depth matters as well. The surface centimeters may be soft and easily disturbed, while the material below may be denser or more strongly bonded. A landing pad or launch support does not interact with only the top visible grains. Load spreads downward. The response of the ground depends on the layered structure below the footpads or support base. A site that looks smooth from above may still contain hidden variations in compaction or buried rocks that influence how weight is carried. For this reason, understanding Martian soil is partly a problem of what lies just beneath the visible surface. When the engines ignite, the regolith faces a second and more violent challenge. Rocket exhaust striking the ground creates plume surface interaction, meaning the coupled behavior between the engine plume and the soil below it. The hot, high-speed gas does not simply blow harmlessly across the surface. It can erode the soil, entrain particles into the flow, excavate shallow pits, and hurl grit and small debris outward. On Mars, the surrounding atmosphere is thin, which changes plume expansion and surface interaction compared with Earth. The exhaust can spread and strike the surface in ways that depend on engine height, thrust, nozzle design, and the local properties of the regolith. The result is a complicated process in which gas and granular material affect one another together. This matters because ejected particles can damage the vehicle itself. Small grains moving at high speed can strike tanks, nozzles, sensors, cables, radiators, and nearby equipment. Dust and grit can also contaminate mechanical joints and expose surfaces. If the launch site is part of a larger surface base, the risk extends beyond the ascent vehicle. Nearby habitats, instruments, solar arrays, and stored supplies may also be exposed to abrasive or coating material driven by the exhaust. The ground beneath the rocket can therefore become a source of hazard precisely at the moment of departure. The regolith also changes the way thrust loads are transmitted into the immediate environment. If erosion begins unevenly, the surface under one side of the vehicle may change shape faster than under another. This can alter local support conditions during the earliest moments of ascent, when the vehicle is just beginning to unload its weight from the surface. A well-prepared pad could reduce this risk, but an unprepared natural site leaves more uncertainty. The soil is not merely present, it participates in the launch event. For a mission returning from Mars, the physical nature of the regolith becomes inseparable from the act of departure. The ground must support the mass of the vehicle, resist sinking and tilt, and then survive the intense assault of rocket exhaust long enough for ascent to proceed safely. Mars offers no concrete pad unless one is brought or made. It offers a natural granular surface of varied strength, varied texture, and incomplete certainty. In this region of the problem, the barrier to getting home lies directly underfoot, in a layer of broken planetary material that must serve first as foundation, and then as the first thing the engines strike. At the surface of Mars, beyond the shape of the ground and beneath the thin moving air, another barrier settles over every structure that waits to leave. This barrier is temperature. Mars is a cold planet, but its cold is not simple or uniform. The surface can warm under daylight and fall to far lower values after sunset because the atmosphere is too thin to store and redistribute heat as effectively as Earth's does. The result is a place of strong thermal cycling, meaning repeated swings between warmer and colder conditions over time for a return mission. This thermal environment matters because the vehicle does not exist only as mass and propulsion, It exists as metal, composites, seals, wiring, tanks, coatings, batteries, and joints, all of which must survive repeated changes of temperature without losing function. The thin atmosphere of Mars allows sunlight to heat the ground by day, but it offers only limited insulation once the sun is gone. The surface then radiates heat away efficiently into space. This leads to large differences between day and night temperatures in many locations. The exact values vary with latitude, season, surface type, and dust conditions, but the general pattern is well established. Mars can be bitterly cold at night and noticeably less severe during the day, especially where sunlight falls strongly on dark ground. A launch system placed on the surface must therefore endure not one steady climate, but a cycle of contraction and expansion repeated over many sols, the Martian solar day. This cycling acts first on materials through thermal expansion. Most materials change size when their temperature changes. When warmed, they usually expand. When cooled, they contract. If all parts of a structure change by exactly the same amount at exactly the same rate, the effect would be manageable. In real vehicles, different materials expand differently. Aluminium, steel, carbon composites, polymers, glass, and ceramics all respond in their own ways. Even different parts of the same metal structure may warm or cool at different rates, depending on their thickness, color, orientation, and exposure to sunlight or shadow. This creates thermal stress, meaning internal force caused when parts of a structure attempt to change size in incompatible ways. Over time, repeated stress can contribute to fatigue, cracking, distortion, or loosening. The problem is especially important at interfaces, where one material meets another. A metal flange joined to a polymer seal, a glass window set into a frame, or a composite panel attached to a metallic support may all experience repeated differential motion as temperature changes. On Mars, where cold can be intense and persistent, those interfaces must keep their integrity through many cycles before the moment of ascent ever arrives. A seal that is flexible enough when warm may become stiffer and less compliant when cold. An adhesive that bonds well within one temperature range may lose part of its desirable behavior outside that range. Engineers can choose materials and designs to reduce these risks, but the environment remains an active test of every such choice. Elastomeric seals deserve particular care. These are sealing materials that rely on elastic deformation to close gaps and hold pressure. In very cold conditions, elastomers can harden, shrink, or lose some of their ability to conform to a mating surface. If a seal no longer presses properly into place, leakage may begin. In a Mars return system, leakage is not a minor annoyance. Propellant lines, gas storage systems, pressure vessels, habitat interfaces, and environmental control systems all depend on reliable sealing. The surface cold of Mars therefore reaches inward into the most intimate boundaries of the mission, where contained fluids and gases must remain contained. Metal tanks and pipes face a related challenge. Their dimensions shift with temperature, and their contents do as well. A stored fluid may contract when cold and expand when warmed. Pressure can change accordingly, especially in closed systems. Cryogenic propellants, if used in some architecture, would present additional demands. But even non-cryogenic fluids and gases require careful management under repeated surface temperature swings. The tanks themselves must tolerate both internal pressure and external thermal cycling without developing cracks, unacceptable stress, or degraded insulation performance. Every stored substance on Mars becomes part of a thermal problem as well as a chemical one. Batteries and electrical systems also live inside this environment, Electrochemical performance generally declines as temperature falls. Internal resistance can rise, reducing available power and making charging and discharging more difficult. Electronics may require heaters or insulated compartments to remain within acceptable operating ranges. Wiring insulation must remain flexible enough not to crack, and connectors must retain contact quality despite contraction and expansion. A return vehicle waiting on Mars is therefore never merely parked. It must be thermally managed even while standing still, because cold does not pause simply because the vehicle is not moving. Lubricants and moving parts face similar stress. A bearing, hinge, valve, or actuator that functions smoothly at one temperature may become more resistant at another if lubricants thicken or if clearances change. The low pressure of the Martian environment further complicates ordinary assumptions about evaporation, outgassing, and heat transfer. Components that rely on motion must therefore be selected and tested for a range of cold and warm conditions wider than many terrestrial systems ever experience. The vehicle cannot wait until launch day to discover that a valve opens sluggishly after a night of severe cold. Dust adds another layer to this material problem. Settled dust changes surface properties by altering color, texture, and the way a component absorbs or emits heat. A clean reflective surface can become darker or more absorptive when coated with fine reddish particles. Radiators meant to shed heat efficiently may perform differently if dust changes their emissivity. The ability of a surface to emit thermal radiation. Windows and optical covers may transmit less light. Mechanical joints may hold dust in places where wear grows more likely. In this way, dust and temperature become linked. Dust does not merely dirty the vehicle, it can change how warm or cold parts of the vehicle become. The thin atmosphere of Mars makes thermal control more dependent on radiation and direct design than on the helpful buffering that air sometimes provides on Earth. Convective heat transfer exists on Mars, but it is weaker. A shaded component can remain very cold. A sunlit surface can warm sharply. The difference between sun and shadow on the same vehicle may be considerable. This means that a return system must manage not only daily averages but local gradients across its own body. One side may face sunlight while another remains turned toward the cold sky. The resulting thermal map is uneven, and unevenness is often what materials dislike most. For a mission seeking to rise from Mars, the surface environment is therefore a long and patient test of matter itself. Every cycle of day and night asks structures to expand and contract. Every cold period asks seals as batteries, joints, and coatings to keep working despite stiffness and stress. Every layer of dust threatens to alter heat balance and wear behavior. None of these effects alone makes return impossible. Together they form a persistent material barrier. Before the engines ignite, Mars has already been working on the vehicle for weeks or months through cold, warmth, repetition, and dust, asking every component the same quiet question of survival in matter rather than in motion. At the surface of Mars, after ground, weather, dust, and thermal stress have all shaped the conditions of departure, the return problem narrows further into chemistry. A vehicle can only leave Mars if it has the means to produce thrust, and thrust in a chemical rocket depends on propellant. Carrying all return propellant from Earth is possible in principle, but it greatly increases the mass that must first be launched from Earth, sent across interplanetary space, landed on Mars, protected on the surface, and then trusted months later for the journey home. This is why the next barrier lies in making return propellant from local resources. The surface of Mars is poor in easy abundance, yet it offers two materials of central value. One is carbon dioxide in the atmosphere, the other is water, if it can be found and accessed in useful form. The atmosphere of Mars is mostly carbon dioxide. This gives the planet an unusual advantage for chemical production. Carbon dioxide contains carbon and oxygen, both of which matter for propellant systems. Water contains hydrogen and oxygen. If carbon dioxide and water can both be processed, then the ingredients exist for one of the best studied return propellant plants, methane as fuel and oxygen as oxidizer. In a chemical rocket, fuel is the substance that is oxidized. An oxidizer is the substance that provides the oxygen needed for that reaction. On Earth, oxygen is drawn freely from the air for breathing, but rockets cannot rely on the surrounding atmosphere in space or on Mars because the air is too thin and unsuitable. They must carry oxidizer with them. For this reason, oxygen is not a secondary convenience. It is usually the larger mass share of the propellant system. The first step in such a plan is gathering carbon dioxide from the Martian atmosphere. Although the air is thin, carbon dioxide is abundant within it because it makes up most of the atmospheric composition. Compressors or pumps can draw in this gas and raise its pressure for processing. The thinness of the atmosphere means that a large volume of air must be handled to collect a given amount of material. This is a practical burden. Machines must run for long periods, filters must tolerate dust, and the system must operate in cold conditions with high reliability. Still, the supply itself is widespread. A mission does not need to search the landscape for carbon dioxide. It is already present above the launch site. Water is less straightforward. Mars contains water in several forms, but not all are equally accessible. Water ice is known to exist at the poles and in many subsurface regions at higher latitudes. Some lower latitude areas may also contain buried ice or hydrated minerals, meaning minerals whose structure includes water or hydroxyl groups. A return mission that depends on local water must therefore choose a site with resource access in mind, or bring part of the needed hydrogen from Earth. Water on Mars is not absent, but it is unevenly distributed and often locked within cold ground rather than lying exposed and liquid on the surface. This makes extraction a mining problem as much as a chemical one. If water can be obtained, it can be split into hydrogen and oxygen by electrolysis. This process uses electricity to separate water into its elemental components. The oxygen may be kept as oxidizer. The hydrogen may be combined with carbon dioxide in the Sabatier reaction, a well-known chemical process in which carbon dioxide and hydrogen react to form methane and water. The water produced can be fed back into the system and split again, making the chemistry partly recyclable in flow, even though losses always exist in real machinery. This cycle is attractive because it turns the local abundance of carbon dioxide into a useful fuel when hydrogen is available. In broad outline, the logic is elegant. Carbon comes from the air, hydrogen comes from water, oxygen comes from water and can also in part be obtained from carbon dioxide processing. The final stored propellants become methane and oxygen, both familiar in modern rocket studies because they offer good performance, cleaner combustion than some alternatives, and temperatures that are demanding but more manageable than those of liquid hydrogen systems. Yet the elegance of the chemistry does not remove the operational burden. Every stage requires equipment, power, time, thermal control, and tolerance of Mars dust and cold. Even oxygen production alone is a major challenge. The oxidizer mass in a methane and oxygen rocket system is typically much larger than the fuel mass. For that reason, a mission may gain great benefit if it can make oxygen on Mars even before solving every aspect of full methane production. Carbon dioxide can be split by high-temperature electrochemical methods to release oxygen, as demonstrated in principle by technology tested on Mars. This proves that the atmosphere is not merely a problem for weather and drag. It is also a feedstock, a source of chemical material that can be transformed into something the return vehicle needs. Power becomes central here. Compressing atmospheric gas, extracting water from icy soil, heating reactors, running electrolysis units, liquefying products, and keeping them stored all require energy. A propellant plant on Mars must therefore be more than a set of chemical vessels. It must be part of a full industrial system. Even if small by terrestrial standards, it needs electrical generation, thermal management, control software, pumps, valves, sensors, and long-lasting mechanical reliability. If solar power is used, dust and seasonal sunlight become direct limits on production rate. If nuclear power is used, the chemistry becomes less dependent on weather, but more dependent on the success of a separate complex system. In either case, making propellant means building and sustaining a functioning process plant on another planet. Purity also matters. Rocket engines and cryogenic storage systems are not indifferent to contamination. Water must be sufficiently clean for electrolysis. Methane and oxygen must be produced and stored at suitable quality. Trace dust, reactive impurities, or unwanted gases can degrade catalysts, foul valves, alter combustion, or reduce long-term storage stability. The chemistry of return is therefore inseparable from filtration, separation, and quality control. Mars does not offer raw materials in laboratory form. It offers them mixed with the realities of a planetary environment. Time is another burden. Propellant production on Mars is unlikely to be quick in a crude mission architecture using practical near-term technology. Large masses must be accumulated gradually, often over many months. This means the plant must begin working long before the moment of departure, and may need to succeed before a crew ever commits fully to relying on it. In some mission concepts, the return vehicle is sent ahead, and its propellant is made on Mars before humans arrive, precisely because return cannot depend on hope. The chemistry must prove itself in stored mass. Seen from this region of the barrier, returning from Mars depends not only on rockets but on transformation. Air must become resource, ice or bound water must become feedstock, electricity must become chemical separation. Reactors and storage tanks must quietly accumulate the means of ascent over time. Mars offers the ingredients in partial form, not the finished answer. The problem is therefore not merely to find fuel, but to manufacture a path home from thin air, frozen ground, and sustained engineering discipline. At the center of the return problem now stands the vehicle itself. After the wide geometry of the solar system, the gravity of Mars, the thinning atmosphere, the dust, the ground, the thermal strain, and the chemistry of making propellant have all narrowed the challenge. The barrier comes to rest in one machine that must do the work. This machine is not merely a rocket in the abstract. It is a carefully balanced body of tanks, engines, structure, insulation, plumbing, guidance equipment, power systems, and pressurized volumes, all arranged under one severe rule. Every part added to make the vehicle capable also makes the vehicle heavier. Every increase in mass then asks more of the propulsion system. The return craft becomes difficult because it must be complete enough to survive Mars and rise from it, yet light enough to do so successfully. Mass is the governing quantity here. A return vehicle has dry mass, meaning the mass of the hardware itself without usable propellant, and wet mass, meaning the mass when propellant is loaded. The dry mass includes the structure that holds the craft together, the engines that provide thrust, the tanks that store propellant, the avionics that guide the flight, the thermal protection and insulation that keep systems within limits, and whatever pressurized or protected internal space is necessary for the mission architecture. The wet mass includes all of that, plus the propellant required for ascent from the Martian surface, departure from Mars, course adjustments, and whatever later maneuvering is still assigned to the vehicle rather than to Earth-based recovery systems. The relationship between dry mass and wet mass is one of the oldest and hardest truths in rocketry. A rocket must carry the mass that it will later throw away as exhaust in order to accelerate the remaining mass. This creates a compounding effect. If the mission needs more propellant, the tanks must be larger or stronger, which adds dry mass. If the tanks are larger, the structure supporting them may also grow heavier. If the vehicle is heavier overall, the engines may need more thrust or more burn time, which may add further mass in engines, feed systems, or structural reinforcement. The return craft is therefore not designed by simply adding desirable features until the list is complete. It is designed by constant negotiation between function and weight. Every kilogram saved in structure or equipment can echo through the entire system by reducing the propellant burden. Every kilogram added can echo in the opposite direction. Engine performance becomes central because mass alone does not decide what the vehicle can do. The propulsion system determines how effectively stored propellant can be converted into useful change in motion. One key measure is specific impulse, which describes how efficiently a rocket uses propellant. Higher specific impulse means that a given mass of propellant can produce more effective impulse. In practical terms, a more efficient engine eases the mass problem because less propellant may be needed for the same mission change in velocity. Yet higher efficiency often comes with trade-offs of its own. Different propellant combinations, chamber conditions, pump systems, ignition methods, and storage temperatures all influence the final architecture. No engine is simply better in every respect. The vehicle must use a propulsion system whose efficiency, reliability, storage needs, and operational demands all fit the Martian environment. Methane and oxygen are often studied for Mars return because they offer a useful balance. They can provide strong chemical rocket performance. Methane can, in principle, be made from Martian carbon dioxide and locally obtained water, and the propellants are more manageable in storage than liquid hydrogen. Even so, they remain cryogenic in the broad engineering sense of requiring low temperatures, especially oxygen, and they do not store themselves without difficulty on a planet with dust, heat loss, sunlight, and long mission durations. Tanks must limit boil-off, meaning unwanted evaporation from heat leak. Insulation must perform through day and night cycles. Valves, lines, and seals must remain functional after long exposure. A return vehicle therefore carries not only propellant, but the burden of preserving propellant in usable condition until the exact day of ascent. Tank design reflects this burden directly. Propellant tanks must be light enough to avoid wasting mass and strong enough to hold internal pressure and launch loads. They must resist thermal cycling, protect against leakage, and maintain suitable conditions for the fluids inside. On Mars, the vehicle may stand loaded for some time while awaiting the proper departure window or final checkout. This means storage is not a brief pre-launch state alone. It can be an extended period of guarded readiness. The propellant must remain where it belongs, in the correct phase, at acceptable pressure, with contamination kept low and with the plumbing ready to feed engines cleanly at ignition. The engines themselves must also match the mission in a precise way. A vehicle rising from Mars needs enough thrust to overcome local gravity and accelerate upward with margin. If the thrust is too low, the rocket wastes propellant fighting gravity for too long during ascent. If the thrust is very high, structural loads and control demands may increase. Designers therefore seek an appropriate thrust-to-weight ratio, meaning a balance between engine force and vehicle weight at launch. On Mars, this ratio can be lower than what Earth launch vehicles often require, because Martian gravity is weaker and the atmosphere is thinner. Yet it cannot be chosen casually. The vehicle still needs a clean, controllable climb from the surface, through the lower atmosphere and into a trajectory that supports orbit, escape, or both depending on the architecture. Staging may help solve part of the mass problem. A staged rocket sheds empty tanks or engine sections after they are no longer useful, allowing the remaining vehicle to continue with less dead weight. This principle has been central to rocketry since its early development. For a Mars return vehicle, staging can reduce the required total launch mass from the surface, but it also introduces more parts, more separation events, more interfaces, and more failure points. A single-stage vehicle is simpler in concept, but often heavier and harder to close mathematically for a demanding mission. A staged vehicle is more efficient in mass but more complex in operation. The design choice becomes a measure of how much complication is acceptable in exchange for better performance. Guidance and control systems belong to the vehicle mass as well, even though they do not produce thrust. Sensors, computers, inertial units, reaction control thrusters, and actuators allow the craft to hold attitude, steer through ascent, and place itself accurately into the needed path. A return from Mars cannot tolerate a large directional error simply because the engines were strong enough. The vehicle must rise not only powerfully but precisely. Precision, however, comes with hardware, wiring, and software, all of which add mass and demand power. The machine must therefore carry intelligence as well as thrust, and the intelligence is never massless. The same is true of structural margin. A return vehicle cannot be built to the thinnest theoretical limit if it is to survive vibration, thermal strain, handling loads, and the uneven realities of another planet. Engineers include margin because real systems are not perfect, and because uncertainties remain in materials, environments, and operation. Yet margin is itself mass. The stronger the structure, the more it weighs. The lighter the structure, the less reserve it may have against the unexpected. This makes the vehicle a continuous compromise between strength and liftability. Seen from this innermost mechanical region, the difficulty of returning from Mars condenses into one exacting object. The vehicle must be light but not fragile, efficient but not impractical, powerful but not wasteful, well insulated but not overweight, and capable of storing the propellant that its own mass constantly threatens to consume in excess. Every system within it leans on every other system. Tanks influence structure, structure influences engine needs influence propellant mass influences tank size, and all of it must still rise from Mars and continue onto the path toward Earth. Here the barrier to getting home is no longer spread across sky or soil. It is gathered into the machine itself, where the physics of mass and propulsion meet without mercy and without simplification. At the innermost point of the return problem, the barrier is no longer mainly a planet, an atmosphere, a machine, or a chemical process taken one by one. It is the narrow margin within which all of them must work together for human beings who cannot safely wait forever. A crewed return from Mars is difficult because every outer layer of difficulty finally converges inside a living system. The vehicle must haunt it must also carry air to breathe, water to drink, means to control temperature, ways to remove carbon dioxide, electrical power, waste handling, communication, and protection against the cumulative strain of long isolation. The final barrier lies in the fact that these needs are continuous. A rocket may burn for minutes. Human requirements continue every hour. life support, in simple terms, is the collection of systems that keeps a crew alive in a hostile environment. It includes oxygen supply, carbon dioxide removal, water management, temperature and humidity control, food storage, waste containment, and pressure control. On a short mission in Earth orbit, some of these needs can be met with generous resupply and fast rescue options. A Mars return allows neither. The crew stands on another planet, far from immediate help, dependent on systems that must keep working through the last preparations on the surface, the ascent itself, and whatever time follows before rendezvous with the next transport stage or direct return path. In this region of the problem, reliability becomes as physical as fuel. Reliability means the likelihood that a system continues to perform its required function over time without failure. For a crewed Mars departure, reliability is not merely a desirable engineering quality, it is a survival condition. A valve in a propellant line may be critical for ascent, but a pump in a water recovery loop may be just as critical if the crew must wait longer than planned. A sensor error may complicate guidance, but a fault in cabin pressure control can become immediately dangerous. Because the return system contains many interdependent parts, the failure of a small component can matter far beyond its own size. An electrical connector, a software timing fault, a degraded seal, or a clogged filter can become important not because it is dramatic, but because margins are small. Redundancy helps reduce this vulnerability. Redundancy means providing more than one path to an essential function, so that a backup can take over if a primary part fails. Yet redundancy has a cost in mass, volume, power demand, and complexity. A second pump weighs something. Additional filters require storage. Extra wiring and backup electronics add their own failure points, even while improving resilience overall. The crewed return vehicle therefore cannot become safe by duplication without limit. It must choose carefully which functions are so essential that backups are worth the burden, and which risks must instead be reduced through simplicity, inspection, or careful maintenance. This is the narrowest form of systems design. Survival depends not on perfection, but on the correct distribution of imperfection. Time intensifies all of this. A crew on Mars does not only need a vehicle that can launch, it needs a vehicle that can remain launchable until the proper moment arrives. A return window may be narrow, surface conditions may force delays, dust may reduce power or visibility, minor faults may require diagnosis and repair. During all of this, consumables continue to be consumed. Oxygen tanks slowly empty. Water stores must be recycled with high efficiency. Food reserves diminish. Batteries age. Seals continue to undergo thermal cycling. Human bodies continue to need rest, warmth, and stable pressure. The final barrier is therefore not only whether the system can perform on its best day, it is whether it can continue to remain within safe limits on ordinary days and on delayed days. Human physiology sets another firm boundary. A crew returning from Mars has already spent many months in transit, many more on or near the surface, and then faces ascent under partial gravity followed by further travel in deep space. The body changes during long missions. Bone and muscle can decline in reduced gravity, radiation exposure accumulates, sleep, mood, attention, and immune function may all be affected by confinement, distance, altered day-night cues, and operational stress. These effects do not make return impossible, but they narrow tolerance. A system that requires constant perfect performance from an exhausted or physiologically burdened crew is not a robust system. The vehicle and mission plan must therefore be designed for people as they are likely to be after a long expedition, not as they are on the first day of training on Earth. Repairability becomes part of this inner margin. Machines on Mars cannot depend on immediate replacement from Earth. Components may need to be inspected, serviced, reset, isolated, or worked around using what is already available. This means the return system must be understandable enough for the crew to manage and accessible enough for them to reach important parts. A hidden failure inside an inaccessible volume is more dangerous than a visible problem that can be isolated. Simplicity, modular design, fault detection, and clear procedures all reduce risk, but each one must fit within the same mass and complexity limits that constrain the vehicle itself. Coordination is the final demand. Launch day for a crewed return requires the alignment not only of Earth and Mars but of all local systems at once. The propellant plant must have succeeded. The stored methane and oxygen, or other chosen propellants, must remain in usable condition. Power must be available. Guidance systems must agree. Weather and dust conditions must be acceptable. The crew must be healthy enough to fly. Surface support equipment must complete its final tasks. The ascent vehicle must ignite and rise within a mission architecture that may also require rendezvous with another spacecraft in Mars orbit, or later interception of a return transfer stage. Every layer of the mission presses inward upon the same moment. This is why the barrier to returning from Mars can seem larger than any single number of kilometers, kilograms, or seconds. The deeper difficulty is integration under constraint. A crewed return asks a chain of systems to function together after months of exposure to cold, dust, delay, and use, with no large reserves of rescue, and with celestial timing that does not bend for human need. The mission may be possible. Many studies show credible pathways, yet credibility does not mean generosity. The margins remain tight because the crew lives inside the machine, and the machine lives inside the physics of Mars. At the innermost threshold of the whole problem, returning home means preserving a brief interval in which air, water, power, propulsion, timing, health, and reliability all remain sufficient together. The final barrier is therefore not one wall but one narrow condition of wholeness, and the crew can leave Mars only while that wholeness still holds. The journey back from Mars rests, in the end, on many layers held quietly together. First comes the wide separation of planets moving around the Sun. Then come the slower rhythms of orbital timing, the long arc of return, the gravity of a smaller world, the fading atmosphere, the weather, the dust, the shape of the ground, the nature of the soil, the cold that works on every material, the chemistry that turns local matter into stored propellant, and the machine that must rise despite its own mass. At the center of all of it remains a human crew, living within narrow margins and depending on systems that must continue to function without relief from distance. Mars does not prevent return by any single impossible law. It does so by combining many lawful difficulties into one exacting whole. Each difficulty on its own can be studied, measured, and partly mastered. Together they create a mission in which almost nothing is casual. The path home exists, but it must be prepared with patience, carried with discipline, and preserved through months of exposure to a planet that offers little forgiveness. In this quiet view, the physics barrier to returning from Mars is not a dramatic wall in space. It is a layered accumulation of distance, motion, matter, time, and human need. To come home from Mars is to pass outward once more through all of those layers in reverse, beginning from a small place on a cold surface and trusting that every condition remains just sufficient for departure. That is why the return is hard, and why it remains one of the clearest measures of how deeply a civilization can work with the realities of another world.